Okay, in this video, we're going to take a look at some comparisons that we can make, some observations that we can make about the rank of a matrix, about its row space and its column space, about dimensions, about the rank in various forms. So we're just going to draw some connections between these things. We've got a matrix A here, and I'm going to very quickly find its rank. And that is quite easily done by reducing it to row echelon form. It's going to make this 1, negative 2, 0, 1. I did this before we started so that I would have it. 0, 1, 1, negative 1. And the last row is 0, 0, 1, 3. And then we need to find the pivots of this matrix. There's one there, there's one there, and there's one there. So we can say, I'll make a list of things over here. The rank of A is equal to 3 because there are 3. That's the easier way to do it. We could have found the rank by using the determinant method, but with a matrix like this, it's easier just to put the matrix into echelon form and find the pivot columns. All right, now let's find the rank of a transpose. Let me write a transpose out here. Where I had a row, I'm going to make it a column, so I'll have 1, negative 2, 0, 1, 2, 1, 5, negative 3, 0, 1, 3, 5. Not done a very good job there. Hopefully it makes sense. And I want to row reduce this as well. When I try to do this on my calculator, I get an error. And the reason for that is that there are more rows than there are columns. And the calculator can't cope with that. So there are a couple of different ways we can proceed. One is to do it by hand. So let's just do that. It's not a difficult one to work on. I'll do the work over here and then I'll erase it because we won't need it. So let's see, I'll just rewrite the matrix. 1, 2, 0, negative 2, 1, 1, 0, 5, 3, and 1, negative 3, 5. You'll notice that I'm reading these as rows now rather than the columns that I used to create them because I'm actually going to be doing elementary row operations to reduce it. To find the pivots, I only need to reduce it to echelon form. It doesn't have to be reduced echelon form. So let's get started. Let's see, I think I'll leave row 1 as it is. It has a pivot in the first position, so that's good. So does row 2, but if I take the opposite, sorry, not row 2, row 4. If I take the opposite of row 1 and add it to row 4, I will get 0, negative 1 plus 1. Negative 2 plus negative 3 gives me negative 5, and 0 plus 5 gives me 5. And then I'll copy in these other rows. And then I'll reduce that one. Let's see, I've got row 1 is 1, 2, 0. Let's take negative 2 times row 1 and add it to row 2. Negative 2 times 1 is, positive 2 times row 1 and add it to row 2. Positive 2, 4 plus 1 is 5, and 0 plus 1 is 1. 0, 5, 3. And then I'm going to scale at the same time. I'm going to scale row 4 by multiplying it by negative 1/5. And I get that. So now I've got a pivot in row 1. 1, 2, 0. I have a pivot in row 4. So let's move that. 0, 1, negative 1. We'll move that to row 2. Let's take the opposite of row 2 and add it to row 3. Let's take the opposite of row 3 and add it to row 2. Doesn't really matter, but if I take the opposite, 0 plus 0, negative 5 plus 5, and negative 3 plus 1. And lastly, 0, 1, negative 1. Now, if I take the opposite of row 4, no, let's do it the other way around. Let's take the opposite of row 2 and add it to row 4. I get 1, 2, 0, 0, 1, negative 1, 0. Let's scale row 3 as we go here. This is taking 2 steps at once, but that's okay as long as and ideally I'd be recording each of the steps that I took here, but mostly we're going to do these on the calculator, so not recording the steps here because I'm really just doing this to show you what I get so that when I show you the calculator trick to get around the error, you'll believe that the answer is the same. Okay, where was I? I'm scaling row 3. I'm going to multiply row 3 by -1/2. That gives me that. And I was also adding the opposite, -1 times row 2 to row 4. Since they're the same, what I'm going to get is a row of zeros. Now, that's all I need, because if I take a look at this in this form, I can see that there are 3 pivots. And so I can add to my list up here the rank of a transpose is also 3. I'm going to be erasing all of this in a little while here. So we'll have more room up here. But I want to take this one step further, because although this is in echelon form and it's given me the information I need, there are 3 pivots, and so the rank of a transpose is also 3. When you find an echelon form of a matrix, it's not necessarily unique. So I'm going to find the reduced row echelon form so that when I compare it to the one I get on my calculator, it will be the same. Like if I find an echelon form of this matrix on my calculator, this is not what I get. I get, let's see, the calculator ended up with a 1s here and all zeros down here, but there's a -1/2 here and a -1/2 here, and then a negative. It's about to close on me. Come back. There's a 3/5 in this position. So, but the reduced row echelon form will be unique. So I'm going to go ahead and keep going. This is row equivalent to, let's take the opposite of row 3 and add it to row 2. There's row 3. Row 2 then becomes 0, 1, 0. And let's take the opposite. Let's take -2 times, I really am cheating here now, but let's take the opposite of, which one? I guess this one here. The opposite of this row 2 and add it to row 1. Sorry, not the opposite. -2 times this plus row 1 would give me 0 plus 1, -2 plus 2, and 0 plus 0. And that is in reduced row echelon form. And again, obviously, I still have 3 pivots. And you can get a lot of the same information. I have a 0 row in both versions of the matrix, the echelon form and the reduced echelon form. But when I do this on the calculator, this is the reduced row echelon form. This is the same answer as I get. But how do I get it? And the answer is, let me just go ahead and write this down first so I can erase the other side. I have 1, 0, 0, 0, 0, 1. No, I don't. 0, 1, 0. 0, 0, 1, and then a row of zeros. So that is row equivalent. A transpose is row equivalent to this matrix here. And I'll highlight my pivots. Okay. Now, what do you do on the calculator? Let me erase some of this. In order to do this on the calculator, when you just type in the original matrix, this matrix right here, and ask it to do reduced row echelon form or just echelon form, it's going to return an error. And the reason for that is that there are too many rows. There are more rows than there are columns. So what we're going to do is we're going to introduce a column. I'm going to use a different color because this really is kind of a trick. We're going to introduce a column of zeros, which gives the calculator the dimensions that it needs. And when you do this on the calculator, you end up with this reduced row echelon form: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. And I could, in fact, have made all of these the same yellow color, right? And then we just say, well, I'm going to ignore my extra input and I'm going to ignore my extra output. And you end up then with the same reduced row echelon form as you did when you did it by hand. So my point in doing it by hand was to convince you when I did it this way that the answer you get here will give you the same result as you would get if you did it by hand, assuming you don't make any mistakes, right? Just echelon form might not be the same on your calculator as the one you do by hand. We have found the rank of A and the rank of A transpose are both 3. Okay, before we go on, I want to take a minute and remind you of a few things here. One is that, I'm going to write in here M by N. A is an M by N matrix. The definition of a column space of a matrix A is the product of the matrix with a vector X, where this product comes from M space, right? This product is in Rm, but the matrix X comes from Rn. Now, if M and N are the same, we have a square matrix, then the product is a vector in Rn, and the vector itself has come from R, or the X vector has come from Rn, the variable vector. But in the case that they're not the same dimension, right, this product is in Rm, but the vector X, the variable vector, comes from Rn. And here's what one of them looks like. Some vector a sub 1, remember that is just a vector in Rm, so it'll be something like this. A sub I, a sub j, all the way up to a sub m times x sub 1 plus, and this one's going to be a sub p, a sub q, all the way up to a sub, I'll call this m sub 1 and this m sub 2. Right? Notation can get messy, but it can be useful to clarify something, but it sometimes has to get really messy in order to do that. Every component in each of these vectors is a number, and potentially every single one of them is a different number. So I've used different subscripts here to indicate that the actual number in this position could be different from the number in this position, and so on. I want to indicate that there are m components in this vector, so I've used a sub m here, but then I have to use a sub m here as well. So I've put a subscript on the m to indicate that this value is different from this value. Anyway, I apologize, it's a little bit messy, but the idea is just to remind you that this is an m-dimensional vector. And again, I've kind of run out of room here, but I should also have times x sub n. Oops, I wrote m, I meant to write n. Okay, so I have the first x component multiplied by every component in this vector. This is a scalar or a weight on this vector. There are m components in this vector, but there are n terms in the sum. Okay, so that's what this means here. X comes from Rm, but x comes from Rn. And so this is what one of those vectors looks like, a generic one, right? If I take a sub 1 to be 1 and a sub n to be 10 and specify some values in here, that's one combination. But if I take different values for my components of A, then I've got a different combination, and I've got an infinite number of them. The column space here is the collection of all such combinations, right? All such linear combinations of vectors with weights, where the vectors are made up of real number components and the weights come from a vector x in Rn, and this product is in Rn. All such combinations, right? So because I have an infinite number of A values, an infinite number of real numbers to choose from for A1, and an infinite number for A2, all the way up to an infinite number of values to choose from AN. There are an infinite number of possible combinations. So that's the column space. A further important reminder here is that when we find the column space, what we have is the space spanned by Rn. So in our example up here, let's go with A. We have a 3 by 4 matrix, so we have an m by n. M is 3, n is 4. Once we find the column space of this matrix, we will have, because the rank is 3, because we have 3 pivots, we will have 3 vectors in a basis. And the basis that we find will span the space that we're in. And here we are in R3, right? 3 vectors here, 3 pivots here, rather. These correspond to, this is just going back to stuff we've done before. If I highlight each column in A associated with a pivot in its reduced form, I get these 3 columns. Those 3 columns form a basis. What do they form a basis of? Well, there are 3 vectors. There are 3 vectors, and each vector has 3 components. So we're in R3. So we have that a basis for R3 is the column vectors 1, 2, 0, negative 2, 1, 1, and 0, 5, 3. So that hopefully will help you understand the sentence at the very beginning of the subtopic rank row space and column space. All the stuff I've done so far, I have 16 minutes, almost 16 and a half minutes, has been a lead up to that. I'm going to read that statement first of all, and then I'm going to try to pull it in from what we've just talked about. Since the linearly independent columns of a matrix correspond to the minimal spanning set of the column space, remember that minimal spanning set just means a basis. So since the linearly independent columns of a matrix correspond to the basis or a basis of the column space, the linearly independent columns of A form a basis for the column space. So what does that mean? We have found 3 linearly independent columns. These are vectors, but they're also columns in A. So because we can say this, these 3 vectors form a basis for R3, we can also say that they form a basis for the column space of A. Now, note underneath this, I'm going to come back to the A transpose stuff in a minute. Underneath this, it says Theorem 6.5.2, given a matrix A, here is our matrix A, the dimension of the column space, remember linearly independent vectors, linearly independent columns, so the dimension of that is 3. The dimension of the column space, denoted by the dimension of, that didn't come out very well, it's supposed to be an M. The dimension of the column space of A, okay, where am I? The dimension of the column space is equal to the rank of A. Okay, so that's kind of a nifty little result. Now we're going to go back and talk about the same thing in regards to the row space. The row space is simply the column space of the transpose matrix. I've written that, I've just noticed, I've written that as a subscript. In fact, it really needs to be a superscript. AT and A transpose. It's just, when I talk about the row space of A, I'm simply talking about the column space of A transpose. So now when I'm talking about this matrix, which is a different matrix, but it's based on the one up here, right? Then when I talk about this matrix, I can talk about the linearly independent columns of this matrix. Those form a basis for, let's write that down here, the basis, a basis for, we discovered that the rank here was 3, so we have linearly independent columns form a basis for R3. And in this case, that is the set negative 2, 0, 1. There are only 3, so we need all 3 of them. 2, 1, 5, negative 3. Let me start that over and make it a little bit bigger. One, negative 2, 0, 1. 2, 1, 5, negative 3. And 0, 1, 3, 5. 0, 1, 3, 5. All right, so those 3 vectors also form a basis of R3. And what that means in both cases is that these three vectors, or these three vectors, span R3. Right? We have the span of R3 in with these three vectors or with these three vectors. These three vectors each have 4 components in them. But in a way, it's kind of like saying, if I have the right vectors in R3, if some of them are not linearly independent, right? If I have, say I have 4 vectors in R3, no, sorry, if I only have 2 vectors in R3, then they're only going to span a plane, right? It may not be the xy plane, but they're going to span some subset of R3, which is R2. Here I've got 3 vectors in R3, so, and because we know they're linearly independent, they span all of R3. Here we have 3 vectors in a higher dimension, but just because they're 4 components doesn't mean that they span R4. In fact, because there are only 3, the maximum space that they can span is R3, because there are only 3 vectors. Okay, now, so since really when I talk about row spaces, I didn't write down the definition of a row space, but here, let me just do it very quickly. The row space, column A, is simply the column space of A transpose. That's it, right? Yes, I could spell it out in the same way as I did this one here, but I don't need to, because all I'm going to do is transpose the matrix and then think about its columns instead, right? Once I do that, the dimension I'm going to find there is the dimension of the row space is the same as the dimension of the column space of A transpose, and so that is equal to the rank of A transpose. So we have kind of almost a couple of little formulas up here that I used the wrong tool there. I meant to grab a highlighter. Right? We have a couple of formulas here now that we can use to find rank or dimension. If we know the dimension of a column space, we can say, well, the rank is equal to that. If we know the rank of a matrix, then we can say, well, the dimension of the column space is equal to that. And the very last thing that I want to take from this is the proof is in your textbook. So because this video is already so long, I'm not going to take the time to prove it here. But the fact that these two are equal is not coincidental. In fact, the theorem, 6.5.4, says the row space and the column space have the same dimension. So we have the column space's dimension and the row space's dimension. The fact that the rank of A and the rank of A transpose are the same is not a coincidence. These are equal, and the proof is under theorem 6.5.4.